You ever stop to think about something that seems super simple but is actually incredibly profound? Like, how does the light from the sun get here? I mean, it has to cross 93 million miles of completely empty space to warm your face. How does it do that? For centuries, that exact question sparked this amazing scientific quest to understand the invisible, to figure out how forces like light and magnetism could possibly travel through a total vacuum. All right, let's dive into this epic scientific mystery. So our story kicks off with a problem that really bothered the great minds of the scientific revolution. See, they were picturing the universe as this giant, intricate machine, kind of like a massive clock. And in a clockwork universe, right, nothing moves unless something else gives it a push.
So, you see the problem, right? If space is truly empty, a vacuum, what's carrying the light? What's the thing that's physically connecting the sun to us here on Earth? To them, it was just common sense. There had to be something out there, even if you couldn't see it or feel it.
And they gave that something a name, the ether. This idea was really championed by the philosopher René Descartes. For him, a true vacuum, just pure nothingness, was totally impossible. He figured the entire universe had to be filled to the brim with this invisible stuff, a plenum, that could pass along pushes and pulls from one spot to another.
Yeah, this quote just nails Descartes' whole worldview. Everything for him boiled down to matter and motion. The idea of a force acting at a distance with nothing in between, that sounded like magic, you know? It just didn't compute in his mechanical world. So the ether was the solution. It was the physical, invisible gear that connected the entire cosmos.
But okay, agreeing that something was out there filling space, that turned out to be the easy part. The real fight, the one that went on for nearly 200 years, was about what light itself actually was. And this debate was basically a showdown between two giants of science. In one corner, you had Sir Isaac Newton. He argued that light was made of teeny-tiny particles he called corpuscles. And in the other corner, you had the Dutch scientist Christine Huygens, who proposed that light was a wave, a vibration traveling through that ether we just talked about. Now, both theories could explain simple stuff like reflection pretty well. But Huygens made a really clever point. He said, look, have you ever crossed two flashlight beams? They pass right through each other without crashing. That's what waves do. Particles, not so much. But honestly, Newton's reputation was so huge that his particle theory pretty much dominated science for over a century.
But you know, science is all about evidence, and you can only ignore it for so long. Over the next century, the tide started to turn. In 1801, Thomas Young did his now famous double-slit experiment, and it clearly showed light waves interfering with each other, creating these classic light and dark patterns. Then a guy named Fresnel came along and nailed the math for diffraction. And maybe the final nail in the coffin for Newton's simple particle theory came in the 1850s. New experiments proved that light actually slows down in water, which was the exact opposite of what Newton's theory predicted. The wave theory was definitely pulling ahead.
Now, while all this drama was unfolding in the world of light and optics, there was a completely different group of scientists in another corner, tinkering with these brand new, kind of weird forces, electricity and magnetism. And nobody knew it at the time, but they were about to stumble on the next huge piece of the puzzle.
I mean, the story of electricity began super simply. The ancient Greeks noticed that if you rubbed a piece of amber, you got static cling. It took centuries, but eventually scientists like Coulomb figured out these forces followed predictable math. And then Ørsted made this wild discovery. An electric current could actually make a compass needle move. Suddenly it was clear. Electricity and magnetism were connected somehow.
But the real game-changing idea came from Michael Faraday. Now, this guy was a brilliant experimenter, but he wasn't a formal mathematician, so he thought in pictures. He figured, okay, if a current can move a magnet, then a moving magnet ought to be able to create a current. And guess what? It did. To explain it, he imagined that the space around the magnet was filled with these invisible lines of force. He thought it wasn't the magnet itself that mattered, but this invisible field that was acting on the wire. This was a totally revolutionary way of thinking about space.
And that brings us to our hero, James Clerk Maxwell. He was a Scottish mathematical physicist who just thought Faraday's work was the coolest thing ever. He basically set himself a challenge. Could he take Faraday's intuitive pictures, his lines of force, and translate them into the rigorous language of mathematics? Well, what he found would literally change the world.
So, you've got these three totally separate-looking branches of physics: electricity, magnetism, and light.
Maxwell's big idea was to see if Faraday's fields could be the thing that connected them all. He took everything that was known about electricity and magnetism and managed to boil it all down into just 4 beautiful, elegant equations.
And this is where it gets absolutely mind-blowing. As Maxwell was working through his own equations, they predicted something no one had ever seen before. A changing electric field should create a changing magnetic field, which in turn creates a new electric field, and on and on and on. This disturbance would shoot through space as a wave, an electromagnetic wave. And the craziest part? His equations could even predict exactly how fast it would go.
So based on nothing more than measurements of electric and magnetic forces done in a lab, Maxwell's math predicted that this new kind of wave should travel at about 300,000 kilometers per second.
Now, at that exact time in history, physicists knew of another speed that was, well, let's just say it was suspiciously familiar, because they had already measured the speed of light, and it was the exact same number.
There's just no way that's a coincidence. It was this incredible aha moment for all of physics. Light wasn't just like a wave, it was an electromagnetic wave. That ancient mystery of what was carrying energy from the sun was finally solved. It was a ripple, a disturbance in the electromagnetic field. It's truly one of the greatest moments of unification in the entire history of science.
So the wave theory of light was confirmed in the most spectacular way you could possibly imagine. But this amazing discovery led to one final, really ironic twist in the tale of the ether, the very substance that started this whole quest. I mean, it's a perfectly logical question, right? If light is a wave, and we all know waves need a medium to travel in, then this has to be it. Maxwell's work must be the ultimate proof that the ether is real. That ghostly medium was finally caught. Or was it?
And here is the fantastic twist. Maxwell's equations didn't need a mechanical, jelly-like ether at all. They just described the behavior of the electric and magnetic fields themselves. The field wasn't just some disturbance in a medium. The field was the medium. It could sustain itself and travel through completely empty space, all on its own, no other substance required.
This quote really puts into perspective what Maxwell accomplished. Even the brilliant Michael Faraday, the guy who laid all the groundwork, thought the idea of describing electricity with waves, the same way we describe light, was some far-off, distant dream. And yet, in less than a generation, Maxwell showed that they were the exact same thing.
And so, solving one massive mystery left us with an even deeper, more profound one. We went from thinking of waves as a jiggle of something, like water, to the idea that a wave could be a jiggle of nothing at all. Or rather, a jiggle in a field. This abstract mathematical thing that fills all of space. What even is a field, and what does it mean for a field to wave? That very question would set the stage for the next great revolution in physics, the one led by Albert Einstein.